Hello everyone and welcome back to our Autodesk robot structural analysis tutorial in which we are going to continue our modeling efforts of industrial warehouses. Now please notice that this video is part of a video series going in tandem in which we are going to cover the theoretical part as well as the modeling aspects of the warehouses, and the link to the sorted playlist is going to be linked top right here. Also notice that I have not posted a theoretical video for this week because so far the theory we have at the moment is enough to continue our endeavors of modeling and designing this warehouse. Now in this video I'm going to talk about some points. I'm going to talk about wind loads, I'm going to talk about gable columns as well as the equivalent horizontal forces. With that being said, sit back, relax and enjoy the show. Now, Autodesk Robot is notoriously weak in the modeling of wind loads. So saving this file as like ASD or something, I will show you that you can actually model wind loads using Autodesk Robot, but it's not what you really think. You can model wind loads by clicking on Generate Wind Loads. Of course, there is a video link top right in which we explain this generation of wind loads here. And the problem with this wind load generation is that it looks cool. You can basically change the values. You can make a wind profile as much as you want at different heights and different wind speeds, which looks cool on paper. The problem with that is that I don't know what code it uses, to be honest. And even if you go to the help of Autodesk Robot, there is no code involved. It does some sort of pressure calculations dynamics, but in the end, when I design something and submit my design for the authorities or to my senior engineer, I might need to prove that I have calculated the wind loads as I'm saying I have calculated them. With this, basically, you cannot just prove what code you use and what pressure factors and importance factors and so on you use. So this is good, this works, but there is no full-fledged reference here to submit to authorities or supervisors to show them that. So that's good, that's nice, but that's not what I try to do today. What I'm trying to do today needs you to basically play a trick. And to play a trick, well, I have opened a new robot file, which is here, and I'm going to start a 2D frame. This is just a small trick I want to play. I would think, wait a minute, 2D frames? Why? What's the idea? I will talk about this in a moment. So, this is my initial structure. The bay is 30 meters. And the height is, I think, 8 to 11.5, right? This is 8 meters, 11.50. This is a 2D frame structure. So I'm going to just take a 2D frame, say 0, 30 in the X, and the Z, 0, 8, and 11.5. Let me just check. Yes, 11.5. And now, wait, why is the 11.5 10%? It's 9.5 now. Okay, 9.5, fine. So let's just cancel here. 9.5 basically, 9.5. And now I can just continue. So I'll apply that. Here is my frame. Now I need still an X and 15 because I need the center point. So here is your center point. I'll apply that and close. And now I am going to draw me a gable. I'm going to draw me a portal frame. I'm just going to draw me something very quickly. So there is my portal frame. Also, I'm going to pin it. I think it was pinned. Apply and close. Now, of course, you're asking, what has this to do with anything related to our 3D portal frame? A lot, actually. If you go to Loads, Snow and Wind, you can now have access to wind and snow in 2D to 3D. If you click on that, now you can define your wind load based on codes. Allow me to explain. I, of course, have to quickly switch to my Euro code very quickly. So units, of course, I'm assuming that you know how to do that. If you don't know how to do that, then check part 1 of this warehouse series. Also check out the 2 videos linked above about preferences and GUI. So I go to database, I go to loads, sorry, design code, loads, and I'm gonna select my wind load to be Euro code. So I'll just go here very quickly to more. I have the British standard Euro code. I will use it. You can use any Euro code you want, any national annex you want. You can use a German annex and so on. I'm going to use the British standard, so I select this, set it as current, okay, and it's as current now. And now I can once again go to loads, snow and wind load, wind 2D. Now the envelope is going to be, just click on auto and it will select you the entire surrounding here. It doesn't have any parapet. The base is on the ground. the total depth is 20 meters. That's not correct. The total depth is not 20 meters. The total depth is, and please notice, a question is, why am I doing this? I'm doing this because if you go to 3D, you don't have access to the wind load from 2D to 3D. You only have access to this when you have a two-dimensional frame. And I don't like using some generic wind load calculation, so I have to improvise. And follow me with this. So my y now is from 0 to 40, which means I don't want to save anything, which means that the depth here is 40 meters. The base spacing is, well, I need to check, is 5 meters? 5 meters. Of course, you're wondering, dear viewer, like, why didn't he do this in the beginning? Why didn't he create his portal frame like this? There was so many nuances I wanted to explain. That's why I just did it step by step. Okay, so I have everything. You can go to parameters now. This is what I mean by Eurocode. You see, here is what you can do, and of course, I'm not going to explain the Eurocode here for you today. There is a video about wind loads using the Eurocode, link top right. What I'm saying is, this is what I like more than this. Like if you go here to your three-dimensional structure, if you go to wind simulation, you see this, which like, where are my typical wind inputs? I have nothing of that. And here you have your typical wind inputs. Of course, here I will leave it for you. You have to, this depends from region to region, how near you are to the sea coast, what the basic wind speed is, and so on. I cannot do anything here because, I mean, I'm currently recording from a place where there is not much wind and there is no snow at all. So, I don't know. For me here, I will leave it as is. I will only use it just to show you that, hey, you can actually select those things and modify them. I will leave it because I don't know what your terrain is. This is something you have to input yourself. Now, I want to 3D generate, not 2D generate. If you click on 2D generate, you get the load on the portal frame, which might be really what you want, but you also want to design the purlins, so you need to know the pressure on the claddings. Can you do that? Well, there are multiple options here. If you know the force pressure on the column, then you can divide by the tributary width to find the pressure on the area. Or you can click on 3D generate, and if you click on 3D generate, of course, he asks you to define your stuff here. I will leave it as is for now, and now it's saving and doing some calculations here. Okay, let's take a look what we have now. Of course, now, unfortunately, it gives you the pressure on the walls and the column. So let me show you. For example, here, you have here a case. There is a million cases here, and believe it or not, you might have to take them one by one. This is annoying, but it is what it is. Of course, here, each case has a meaning, suction cases, and so on. Now, you are pros. I'm pretty sure that you know some cases that are more controlling than the others, but actually, you will have to take each case and apply it on the portal frame. The other option is to, well, perform a dynamic analysis. Now, I'm going to try something very quickly here. If you go to the wind data here, let me just do a comparative analysis very quickly. The wind speed is 21 meters per second, so let's try it here. The wind speed, okay, wait, I think the wind speed was measured at the reference height, right? I forgot what the reference height is, to be honest. I totally forgot. Loads, wind load simulation. I will just leave it as is and say 21 meters per second. And just leave everything. I just want to see how close it is, like with its basics here, and just give pressure from one side. I'll just start this and see what happens. Now it's computing and calculating. I want to see how accurate it is, to be honest, like how close it is from how close this is in comparison to the code. So let's see what happens. Okay, so the analysis is complete here, and let's take a look what happened basically. So it seems that I have suction here and I have pressure here. I mean, if this is accurate, then I'm golden, right? So the pressure is 40 and the suction is here negative 40. So is it correct or not? Well, let's take a look. Based on the 2D analysis, I have those values. So let's just open the load values here. This is wait, what? I need to see it correctly because I don't want to mess up. Okay, so let's say this is 1.68, right? This is 1.68. Now 1.68, really? I think I'm onto something. Let me just go to like the first thing I have here. 1.68. Now, what's the tributary area of this? Like this covers 5 meters in width. So 1.68 divided by 5 is 0.35. And this is 0.4. Okay. Going on, the top side here is 1.39. So 1.39 divided by 5, 0.27. And here, what do I have here? I'm looking now at the right side here. It says 0.41. Now, of course, I have 5 meter spacing. So if you click 0.41 divided by 5, I get around 0.082. If I go to the 3D, like this generalistic one, you have around less than 0.13. So, that's pretty accurate, to be honest. I'm surprised. Okay, now, all right, so I will leave it at the discretion of you, my dear viewer. I will give you now 2 options to deal with this. Option 1 is to use robots analysis, which actually allows you to do a full wind simulation like this. You can make a multiple direction pressure like this, basically X, Y, and so on, which is what actually happens in the code. Like the code actually tells you wind left, right, and CPE positive, negative, and so on. That's what the code does. You can do this, or you can choose to do a 2-dimensional analysis like this according to the code, and this is like watertight, and then take the values you get here and apply them on the portal frame. It's up to you. I just want to tell you again that robot is weak and is a little bit limited in wind load simulation. So I kind of dislike the way that robot is dealing with the issue. Anyway, allow me to show you, just for the sake of completion, how I would apply my wind loads if I do not use robots wind load analysis, but use the code analysis like this. If I use the code analysis like this, of course, you have so many cases. Now this could take ages, so I'll basically choose to show you how to do one case, and I rely on you to do the rest of the cases, because now it depends on your company and your willingness to accept either robots analysis or the analysis of codes. I am going to show you how because robots analysis is ready, you can just use it. I will show you how you could take the results from such an analysis and apply it on your 3D structure. So I'm only going to show you the first wind load case and the first snow load case. That's the only thing I will talk about. The rest you can do yourself. So I will choose the wind load left, right here, and let's take a look what we have here. We have 1.68 and 0.84. This is half of this. No wonder this portal frame is always going to be half of this internal portal frame, because this portal frame covers 2.5 meters, whereas the internal portal frame covers 1.68. So if you take the values of the external portal frame, you have to divide by 2.58 to get the area loads, and if you use the internal portal frame, you will have to divide by 5. So I'll choose to take the external portal frame because I can easily see it. How can I easily see it? Well, I go to 3D XZ, and now I see everything quite obviously. I have 0.84 going from left to right, so with a quick calculation, 0.84 divided by 5 is 0.168. So let's go to the 3-dimensional model, go to load cases, like here, and add me a wind load case. Of course, you would have multiple wind load cases. I will add me here, how can I say this? Manual wind load. I'll add that, close, and then now it's selected. I go to my load, select surface load in the direction of X, and it's 0.168. So in the X, it's 0.168 kilonewton meter. I'll add that and basically apply it here. So that's one load done. What about the load at the surface? You have 2 domains. You have the near domain and the far domain. The near domain is 1.09, the far domain is 0.2. How can I do that? Well, I'll go to my load on contour, and the load here is going to be, now first of all, it is perpendicular to the surface, so it's local. Second of all, what is the local coordinate? I can't say anything because, Okay, that's the global coordinate, is it? Let me just zoom in and out. Small, big. Where is, there we go. This is the local coordinate of the plate, so it's the z-axis I want. I wanted the negative z because, no, in the positive z because it goes up. So positive, it's not 1.09. No, it's 1.09 divided by 5. 1.09 divided by 5 is 0.218. So it's 0.218. Of course, I cannot simply add because I need to define a contour. So I go to contour definition and I start contouring. So that's, oh, I need the distance, right? So I go to design or tools, dimension lines, just to check how long this thing is. I'm of course winging it here. It's 2 meters. So I'll choose 2 meters now. I'm not being 100% accurate here, to be honest. Like I'm just doing it as quick as possible. Of course, being accurate or not is only a matter of timing and the amount of time you will invest in this. Not an amount of, it's not a matter of technique. So that's my first contour. What's this? 2 meters, 3 points, wait, what? 1.88. I'll accept that. You could add a point here to click, but I'll accept this as my accuracy. I select here and close my contour now. There we go. And now I'll apply it to here, and that's my load applied on that thing. This is the high pressure domain. Now I need to do my low pressure domain. So I select load on contour again. This time my low pressure domain is 0.2 divided by 5 is 0.04. So 0.04 still going up and still in the local, right? Yeah. Now I'll go to contour definition and start defining a contour. Once again, I am being approximate here. You could invest more time to get a 100% accuracy in the contour definition, or you can still use the three-dimensional analysis that robot provides. So for me now, I'm just doing it very quickly here. Not a big deal. And there we go. And I click here, and it's applied exactly as I want. Finally, or not finally, I still have 2 domains here. I have, what's this, 0.24 or 0.2? It's 0.24 and 0.2. There's a difference here. Okay, I mean, I'm just gonna put me 1 domain here because I mean, I've just showed you how you can do multiple domains. So 0.24 divided by 5 meters is 0.05. Why am I dividing by 5 meters? Because the portal frame spacing is 5 meters. So I'll just go to contour again, or no, just global, just uniform, local. It goes up in the Z, 0.05. I'll add that, click here, and now I think I messed up. I think I did mess up. What's this? Oh, I see. Okay, I see. Okay, let me just go to loads, load table, and I think that's the one. Yeah, that's the one. I'll delete this and go back. I should not see it now. Yes, I don't see it. Let's repeat again. Uniform planar, local, nothing in X, and 0.05 in Z. I need to make sure where the Z-axis is for that thing. And hope that it works. Yeah, it works perfect. Finally, I have this, which gives you a 0.0. Wow, that's very small. 0.02. It's like ignorable. I can just leave it, but no, let's do it. 0.02 divided by 5 is 0.004 to the left. So this time global. 0.04 to the left means negative in X, nothing in Z. And I'll add that, click here, and that's one case of wind load done. That's how I would do it if I wanted to use the code. So that's one case accomplished. This is one option. Of course, the other option is to basically use the analysis. If you have any better idea for robot, please tell me in the comments because I'm really interested into that. I don't like what robot is doing here. But it is what it is, right? You can't have everything. That's one wind load. I'll go to combination again here and select me a, sorry, I go to load type again, add me a snow load here and add that. And now I will have to do the same, rinse and repeat, the same thing. So I go to surface, go here very quickly, check the snow load. So I'll go to snow load case 1. It's projected load, 0.22. on the end. Of course, there are multiple snow loads. You have to choose like each snow load itself, even accidental. It's kind of cool. For me, I will just use one snow load here, which is this one, 0.22. Remember, I'm not being thorough here. You should apply all the cases. I will only apply one now. 0.22 divided by 5 is 0.044 or something. I mean here, 0.22 divided by 0.22 divided by 5, 0.044, exactly. Going down. So I click on the load definition, surface, load. Now there was a problem with the projected. I remember in one of my videos, I forgot. I think there was a problem. I don't care, robot will still be able to solve it. So going down, negative 0.044, I'll add that, click here, and click here, and that's it. I have applied my wind load and my dead load. I've applied my wind load and my snow load. Did we finish? No, because you still have to apply the equivalent horizontal force. So I will do it for dead and live just to show it. Remember, my dear engineers, the idea of those video series or tutorials is to give you the principles to like go out and explore the world and do it yourself. Like I rely on you to do the entire snow loads and wind loads because I could do it, and this would be a really good YouTube video of 5 hours, of course, which would give me a lot of ad income. But in the end, I don't care about any income. I care about your time. It's your time. I'm wasting your time if I make 5-hour videos. This doesn't make any sense. I'm trying to keep my videos below the hour mark. Okay, so equivalent dead loads, right? How do you do that? Well, I run the analysis, hoping that nothing explodes. It's still stable. Oh no, I have the wind load, right? That will take hours now. Okay, so I have the analysis complete now, and I'll just go to results and go to reactions, or I can just show the reactions by clicking on this, results, diagrams, numbers, reactions, open everything, and give you some descriptions, apply. So you get your reactions. Why do I want the reactions? Because I want to talk about something called accidental loads. Accidental loads, as we have explained in 2 videos, I'm going to link them in top right, are basically loads that are applied to account for accidental eccentricities and I mean, this equivalent horizontal force you try to do is here to account for any global imperfections in the elements. So I've explained this and calculated this in videos before. For this specific portal frame, it's 0.3%. So I take whatever force I see here in the Z and multiply by 0.03%. So I will just choose the largest. Of course, you can be more accurate and choose each one by one. I'll choose the largest, which is like around, let's see, 48, 100, 100, right? Yes, around 100, is it? 103? Yeah, I mean, 100, just if you take 100, 0.3% of 100 is 0.3 kilonewtons. That's nothing. 0.3, really? I mean, it is what it is, right? So 0.3 kilonewtons. So what I did is just I multiplied 100 multiplied by 0.3, the ratio between, wait, what? Oh yeah, 100 multiplied by 0.3%, which is in decimal places 0.003, that gives you a 0.3 kilonewton, which is nothing. I mean, 1 kilonewton, it's like 30 kilograms, that's nothing. But okay, well, it is what it is. So what do? I'll basically remove everything because I want to see now. I go to dead load, and I'm going to apply the accidental dead load on the dead load. Like if I go here, I'll apply the accident, like the reaction I got just now are the reactions of the dead load. So I'm going to apply here an accidental load on the dead load case. So I select my dead load here, and before I continue, yeah, and just basically put 0.3 here in the X going to the right. I'll add that. Do me a nice little trick in selection in which I'm very careful here. Zoom in a little bit, select apply to, select that stuff. I should have 9 nodes because I have 9 portal frames. I'll apply that, and lo and behold, I see the point loads. Of course, there was a nice discussion between me and engineer Khanye talking about the dead loads, that sometimes oversizing dead loads will affect your purlins negatively when you consider other load cases. An example he gave, and I want to elaborate on that, if I understood him correctly. An example he gave was about the uplift forces, because remember, in the wind load, there are loads pushing up, and you have combinations where you have uplift forces with dead load, and it helps the stabilization of the structure. Like, you have to have accurate dead loads, because dead loads, in the case of uplift, are actually a good thing, because the more dead load you have, the more resistant to uplift your structure is. So oversizing my dead load to 1 is something I have done in the last video. It was 0.6 and I put it 1, and I just wanted to mention that, hey, you need to be more accurate than that. Of course, here I'm just explaining everything and hope that you choose the correct decisions that you see fit. Okay, so that's dead load. I go to live load now. Not the crane, I go to the real live load here. I have a cool trick. I go to dead load, the load is 1. I go to live load, the load is 0.6. So my accidental for live load for dead load was 0.3. Yeah, so it was 0.3. If you multiply by 0.6, I get 0.18. That's the dead load for, I just did a small ratio here. That's the equivalent load for live load. So I just go to loads here, select the load, and use 0.18 in the X, 0.18 in the X. I'll add that, close. Are they selected? I think they are. Yes, they are. Okay, so perfect. Now I have done my accidental loads. What else remains? Oh, the best remains right now. The best is for last. You see, I want to give a huge CE-sized shout out. This time, yes, besides the CE members, this time I want to give a huge shout out to all the CE community for their amazing comments. I mean, you can see them on the screen here. All of them correctly commenting and explaining that, hey, your gable column should be rotated 90 degrees, and some of them even suggesting joint or connection details to understand that. So I will show the connection detail very quickly on the screen. The editor is going to do that. And I want to give a huge thank you to all of your colleagues. Like, this is amazing. The discussions I get here is amazing, and that's what CE is all about. It's not just me standing and lecturing here. It's here to have a community. And of course, please notice that any comment you write is going to be read in detail, and I give it the utmost consideration. It's okay. Based on their correctly pointing out, I'm going to take this, go to gamma angle here. Is it here? There we go. I click positive here. You can select all the columns if you want, to be honest, like this, this, and this. I go to gamma angle and put 90 degrees here. Notice there might be more details about this, and feel free to double check that, whatever you want. Now I made this here, and last time I bleeded a lot of time explaining the different aspects of modeling these, and I ended by saying, hey, I'm gonna release it on both sides. Now, once again, all thanks to all of our subscribers, many of you have mentioned that, no, we actually have here a release in the axial. And go to geometry releases, you can make a custom sized release by clicking, for example, here, add. I can add me here a gable column release. And according to your input, as well as what we see in the connection detail, I just have to release at the end UX and all the moments. The torque, I don't think the torque is released, but I don't think there's any torque. I will leave it for now. And I'll add this, close, and now I will switch the release from fixed pin to fix semi-pin. So if I go here, you can see the symbol says FXX, FFF. F means free, XX means not free, and 3 Fs means free. This means movement X is free, movement Y is not, movement Z is not, and all the rotations are free. Of course, I can do the same thing here and the same thing here, and now I run the analysis hoping that it works. At the moment of truth, will it work? I am really, really happy about this. I really want to extend my deepest gratitude to the CE community. Like, we are almost ready to design. Like, what we should now do is to, of course, I'm gonna design like a next video, which is gonna be the final video of this series. But just to mention some things here, I want to quickly talk about some discussion points and some things I wanted to address very quickly. The first discussion point was about our dear subscriber Donald Khanye and member, who correctly said that, wait a minute, you have a moving load here, which is the crane, and a moving load here, which is the crane. And the problem with the moving load definition in the loads, special loads, is that those two moving loads are disconnected, like they don't move in unison, meaning that one of the cases that will get analyzed might have a point load at the very far end on this side and the near end here on this side, which is impossible because the crane moves in parallel. Like if the position of the point load is here, then on the other runway it should be the same position because it's one crane. Now, of course, robot doesn't see that, but I still am somehow not worried. I need to see this, of course, and I need to prove it, but I'm somehow not worried because I'm expecting that the maximum loads will happen on the portal frame when it's maximally loaded, meaning that both crane forces are on the same position. Now, the moving load you need to design your crane runway, if it's your task. If it's not your task, then you're good to go. That's the first issue I wanted to talk about. The second issue I wanted to talk about is also a comment from audio subscribers explaining that you could also model not only the crane load, but also the crane acceleration, stopping and accelerating, which is a horizontal force, by simply adding here a factor. Like if you calculate and realize that the equivalent horizontal force for the crane accelerating and decelerating is like 0.5 of the vertical load, you just put here 0.5 and you're golden. Everything will be working perfectly fine. Of course, we had a different factor here. And the third thing was about having bracings that are compressive. And believe it or not, those do exist. Now, I went to IKEA specifically to see that in action because I wanted to make sure that whatever I say here is happening. Now, of course, the bracings usually are tensile in nature, but you can have compressive bracings, and sometimes you have full trusses as compressive bracings. And I'll just show you some pictures here about IKEA from the internet, something I've seen in my own eyes, where they actually use heavy-duty elements that are compressive resistant in the stabilization of their frames, which is really cool. So this exists, of course. Is it an overkill? Is it not? It depends on your project. Like I told you, there are so many warehouses as many engineers exist. There is no singular warehouse that is correct and everything is wrong. That's another thing. The third thing I want to mention is that I still need to make this become a tension member. I have not done this because I wanted to consider both compression and tension members, and of course your dear viewers have mentioned that, hey, you can do that, but you need to use larger sections. I will leave it to Robot to decide because in the end he will be the one who's designing. Of course, at the design of those elements, I'm pretty sure that Robot will suggest larger sections because of the KL over R issue, which is basically the effective length over radius of gyration. So I'm pretty sure Robot will suggest larger sections. However, since we're discussing this, I'll just show you that you can actually go to geometry, additional attributes, and go to advanced member properties, and you can ask it, the selected elements, to be truss member, only axial force. And if you click on tension compression, then you can select if this truss element is a compression only element or a tension only element. So if your bracings are tension only, which is 99% the case, you can apply tension only members on those. I will leave it because I will address in the design, I hope remember that, I want to address the idea of having compressive as well as tensile bracings, so I'll leave it for the design. Finally, talking about combinations, that's something I will do in the next video. I just want to apologize for being a little bit late on this upload today, but well, it is what it is. So in the next video, we're gonna basically finalize this entire project by having our load combinations, and I'm going to explain manual versus automatic combinations, and then dive into the design of that thing, both connections and and portal frames. Please notice that I have not and I am not intending to. I have not and I am not intending to provide purlins here and put a cladding here. I will leave it open. The reason behind this is because I want to show more details when we're designing. This is not correct because I assume my warehouse to be closed. I have not done this, but you have all the necessary tools and experience to do that. So yeah, I hope that you enjoyed the video and stay tuned for more. Before I finish, I want to give a huge CEE-sized shout out to our dear channel members whose names are going to be shown on the screen. I want to thank them from the deepest of my heart, as their contribution to the channel allows me to push even further and do some more high quality videos. So thank you from the bottom of my heart. So yeah, that's everything. I hope that you enjoyed the video and that it was beneficial for you. If you have enjoyed the video, then please like, share, comment and subscribe, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video.